Hello, everyone. I'm Heidi Walters of the National Association of Energy Service Companies, and I'd like to welcome you to the fourth and final webinar of the year, Blue Light and LED Outdoor Lighting, presented by Bruce Kinsey. There is an AIA CEU available for this webinar, so if you want credits for this, contact me by email, and you can receive a certificate of attendance and an evaluation form. My email is Heidi, Heigi, @nasco.org. If that was Jim, can you mute your phone? I will distribute a recording and a copy of the presentation to everyone probably by Wednesday. So if you have to leave early or if some folks weren't able to make it, I'll make sure everyone who signed up gets a copy. And you can submit your questions through the question feature, but we will take Q&A at the end of the session. So I would like to thank Bruce Kinsey for presenting today. Bruce has worked in energy efficiency and renewable energy for 31 years as a research engineer at the Pacific Northwest National Lab. He joined DOE's solid-state lighting team in 2006, originally managing the Gateway Technology Field Demonstration Program, subsequently developing a focus on street and outdoor lighting applications and associated issues like blue light content. He is presently serving as chair of the Illuminating Engineering Society Sky Glow Calculations Committee. I will now turn the presentation over to Bruce, and thank you all for joining us.
Thanks very much, Heidi. It's a pleasure to present to this group on this particular topic, which is getting lots of attention these days, and hopefully you'll find us of some value. Okay, so the topics that I'm going to cover today continue to generate a lot of interest, not only among the lighting community, but also the general public. Unfortunately, there continues to be a fair amount of confusion surrounding these in terms of their actual impacts and the risks imposed and how all these fit into the larger context of other risks and impacts and so on. So I hope to provide a little clarification on these things today. These topics touch on a lot of very complex issues, things like biological responses and radiative transfer through the atmosphere, where there are almost never simple, clear-cut answers to questions that come up. The questions seem simple, the answers almost never are. And these are just the facts of the matter. And this is despite the way in which these issues are typically being stated, as well as the remedies that are being proposed to resolve them. So I'm not a medical expert, and so I have to qualify everything I'm going to say in that light, and you should take it in that light as well. But I can state the facts as we generally understand them today and let you draw your own conclusions. I'll try to avoid going too far down any rabbit holes in any of these topics, but hopefully can provide enough information for you to have some useful takeaways for when the questions come up from your customers or other folks that you may be dealing with. I guarantee that you will still have questions at the end of this because even the experts still have questions. And frankly, this is a big part of the situation that I don't think is conveyed nearly enough in the media and elsewhere. So with all that said, first I want to illustrate some of the uncertainties and misperceptions that are floating around out there. And I'm going to spend a fair amount of time on this because these are the sources of a lot of the confusion. Then I'll provide some results of efforts that the Department of Energy has undertaken to try to clarify at least the parts that we do have expertise in, and that pertains to the lighting technology side. And then also what these mean for what we think is really a more realistic picture of the overall situation. And then hopefully we'll have, I think we should have about 10 minutes or so at the end for Q&A if we need it. Okay, so street lighting, blue light, CCT, correlated color temperature, are all the talk these days and have been since the AMA brought this to center stage. The American Medical Association brought it to center stage back in June of 2016. Of course, we saw the major media outlets pick this up, and the internet went crazy with it, so did the general public, and so on. This resulted in a significant response from the lighting community, including the Department of Energy. We've spent much effort over the last, me in particular, a lot of effort in the last year and a half producing information resources and tools and documentation that is posted on our solid state lighting website at the address that I've provided there. This is a point that I really want to make clear. It's not that the issues that have been raised don't warrant further investigation. I mean, they're not nonsense, but this release sort of pushed a panic button that the lighting community doesn't feel is justified based on what we know today. It also contains a lot of use of subjective terms and questionable underlying assumptions that really are clearly meant to sway the reader to a particular position. So the document was definitely not up to the AMA's usual, very academic standard. This is probably one of the biggest problems that we had with it. So at this point, I want to provide you at least some general background on the issues that have been raised. Now, this is not going to be a full treatment of the issues by any means, and is fraught with potential rabbit holes that I mentioned earlier that I'm going to need to try to skirt, but I think it's very important to appreciate some of the general mechanisms involved. So we're all familiar with the rods and cones in our eyes that provide visual images to the brain. These have long been known probably by all of us since we learned about them in grade school. But in 2002, researchers discovered another cell in the retina of mammals called the intrinsically photosensitive retinal ganglion cell that is a non-image forming cell, but it relays information about the presence of light and I guess some qualities of that light, such as sort of general spectral characteristics and so on. And that cell thereby plays this important role in the alignment or resetting of our 24-hour biological clocks. So this graph to the right shows the melanopic action spectrum or sensitivity of the IPRGCs to different wavelengths in the visible spectrum. Now there are lots of different action spectrums that affect our eyes. Basically, you see there's different wavelengths along the bottom, and this is just showing the relative level of sensitivity. And this is the curve for specific to this melanopic action spectrum. And you can see, according to the color band that I put along the top there, that the highest sensitivity occurs kind of at the upper end there of the blue range, right around 490. Now, this is an average for the population, so it shifts on an individual basis a little bit on either direction. It'll also change over the course of someone's lifetime as the lenses in your eyes yellow with age and so on. But you can also see that this is the average for the population. But you can also see that there's sensitivity here to many other colors or wavelengths all the way through green and into the yellow there on the right-hand side as the sensitivity level is dropping off, and then over into the ultraviolet on the left-hand side. So this means that most sources of light at night, any that emit light anywhere within this range of wavelengths, have at least some ability to potentially stimulate the circadian response and possibly disrupt the synchronization of the 24-hour clock with potential detrimental effects. Now, I'm emphasizing particular qualifiers here because IPRGC sensitivity is just one factor of many that comes into play, and the others are critical, like intensity of the light source and the period of exposure to it, and also how much normal light the individual has been exposed to over the previous 24-hour period. The Lighting Research Center, for example, Rensselaer, notes that the real problem may be due to our spending most of our days inside buildings and thereby not getting enough exposure to natural sunlight, rather than, say, some out-of-sequence exposure to some trickle of light that's seeping into our bedroom windows at night. Anyway, exposure potentially comes in a couple of ways. One where someone is in the direct beam of a light source, say lying in bed under a curtainless window with a street light streaming in. That's kind of a hard one for me to visualize, but that would be sort of the worst case. But from there, then to also to a lesser extent, from the general brightening of the night sky that is particularly noticeable in a city environment that we typically refer to as sky glow. So as I noted earlier, the potential impacts of these issues appear to be of genuine concern, at least as demonstrated in a laboratory type environment. But a very important need remaining here is to determine how this kind of research result, where someone is staring at a screen like this for extended periods like an hour or more, translates to someone asleep in their bedroom, and with or without curtains, etc., all those kinds of variations. Much of the research results to date have also been generated using these genetically modified and very unfortunate mice subjects, which are mammals, but obviously they have some very distinct differences from humans. And just one example of this is they're nocturnal, so of course they're particularly sensitive to light at night. So just how do these research results using animals like this translate to humans? There's actually a fair amount of contention about this within the medical community itself, and if you're interested in going down that particular rabbit hole, you can Google it. And there's a variability among individuals, or variability even for a given individual, depending on things like their age or their general state of health. What kinds of other risk factors or mitigating factors like diet does the individual engage in, or do they work night shifts, or are they smokers, and so forth. It turns out those are two pretty big factors, which I'll talk a little bit more about in a little bit. So the AMA release leveled its charges specifically at street lighting, as you saw in the title, but there are also lots of other sources of light at night. In fact, you probably can't even find the street lights in this photo, at least without some searching. There are street lights in the photo. So what the research to date has done is identified the potential for health impacts from light at night, but there is no current epidemiological evidence that directly ties, for example, an increasing risk of cancer, which is one of the risks the AMA release mentioned that really caught the public's attention, as you might imagine, to light at night, or separates it from all these other factors. There have been a number of studies of shift workers that have identified correlations. For example, a recent Harvard study looking at more than 100,000 nursing staff and cancer rates and light at night concluded that, quote, although further work is required, so let me say that again, although further work is required to confirm our results and to clarify potential mechanisms, our findings suggest that exposure to residential outdoor light at night may contribute to invasive breast cancer risk, end quote. That's kind of a study in qualified statements, right? It may contribute or it may not contribute. And this sentence followed right after the statement, quote, the light at night / breast cancer association was observed only in past and current smokers, end quote. And there was also a correlation that was found to be more pronounced among those that had done shift work. So as I said before, I'm not a medical professional, so I can't say that there isn't a relationship. And in fact, light at night is there probably is some sort of relationship in terms of it being more of an enabler. Once there's a tumor or something else that's been introduced, it may be allowed to grow if there's a disruption of the circadian rhythms and so on, but it's not a cause of it. That's what it looks like to me anyway. And there's, in any case, there's a ton of uncertainty that remains to be resolved within the medical community. And you heard it in the way that conclusion was stated, and the medical community should and is continuing to research these issues. All right, now I want to briefly switch to the areas that we do have expertise in, specifically the lighting technology, and notably this is where the medical community does not have the expertise. So, of course, this statement came out in the middle of the widespread conversion to LED streetlights, so the natural implication is to assume that the issues apply only to LEDs and only to street lighting, and not so, which I'll demonstrate in a moment. Okay. Here's a direct quote from the release. and I'm not going to read it, you can look at it, but it's effective as an attention getter, but it probably doesn't apply to 95% of the street lighting that's been installed out there in the United States at least. Even at around 4,000 K, which is where the bulk of, the vast bulk of streetlights in the United States reside, these values are half or less that amount. Still not to be ignored, but it's not, not quite as splashy as saying, 5 times. This quote also suffers from a very common but faulty assumption that everything else remains constant in a conversion. So you're just simply substituting, say, a 6500K spectral content for a 1900 or 2000K high pressure sodium spectral content, and you don't change anything else with respect to the light output. This just doesn't track with real world experience. I'm going to show this too in a little bit. Okay, so a central point among all of these discussions, and incidentally, this message finally appears to be getting around out there. We're starting to see more and more people saying this, is that CCT, or correlated color temperature, just isn't a good metric to use in a luminaire specification, for example, if your goal is to limit the potential for the kinds of effects that we're discussing here. I'm sure everybody on the line here is very familiar with color temperature. It describes the appearance of a light source like we see there in the 2 photos. There's the same classroom lighted with a 3000K source and a 5000K source. Color temperature is really essentially a sort of a weighted average of, it's made up of the actual spectra contained or emitted by a source multiplied by the wattage contained in each of those spectra. So when you put all this together, it produces this sort of final score, if you will, which is this nominal color temperature. Okay, the issue here is that just like any kind of weighted average, actually there's, virtually speaking, there's virtually infinite number of combinations of different spectra and corresponding powers emitted in those spectra that could add up to this same score. Practically speaking, it's nothing close to infinite, but there is a pretty wide variability, especially among LED products here. And so it's just not a very specific or precise indicator. There are general trends that follow color temperature, but it's not a precise indicator. And here I've got, as an example, here are 3 different products listed at 4000K. I have a metal halide here, there's a fluorescent, and there's a 4000K LED product. If we were looking at these same photos of this classroom, say, and we had 3 different photos illuminated by each of these 4000K sources, you probably wouldn't be able to tell the difference between them by looking at them. And yet, looking at these spectral power distributions, you can see that the actual content is quite different. And that's kind of the crux of the matter here, is that colors do not cause these issues, spectra cause the issues. And again, this is just a very rough, you just don't have a very good idea of what the actual spectral content is, a very precise idea of what the spectral content is in a source based only on its color temperature. Okay, and that'll become more evident here in this table, which we developed in its original form in direct response to the AMA release. And the purpose here was basically to show that, hey, this is nothing unique to LED. It's nothing unique to exterior lighting. These issues apply to exterior and interior lighting as well. And furthermore, there's nothing new under the sun here, so to speak. So here we have this listing of several different light sources. These are used for both interior and exterior. We have a whole range of color temperatures here. These are all they're all normalized here for luminous flux. So this creates apples to apples comparisons in the table. You see there for the top 8 LED products, which are listed according to their nominal CCT bins. You see that there's 8 categories there. And then as we move on over to the right, you'll see that there are ranges in the properties for these other 3 columns. Those ranges reflect the fact that far from being a monolithic product, there's actually quite a bit of variation among different LED products, even at the same color temperature. And this table now has, underlying those LED ranges, there are more than 450 real product spectral power distributions underlying that total set of all 8 of those. Cumulatively, there's more than 450. And actually, here's how they break out on a per color temperature basis among the different color temperatures. So if we just go over to the right-hand column there, the relative melanopic potential. This is the relative ability. This is a relative table, first of all. So we're talking about street lighting. So still the majority of installations around the United States are high pressure sodium. So we've normalized the values in this table there along row M. And you see, if you go over to the right, you see that has values of 1.0 in those columns. And then all of the other products in this table are being reported relative to high pressure sodium. That relative melanopic potential, that's basically the relative ability to stimulate the IPRGCs. Now, this is not a perfect measure, but it's the best one that the lighting community and the medical community has right now. This will probably be modified in the future, but for now, this is sort of used as a proxy for that ability to potentially disrupt the circadian rhythms of an individual. So let me give a couple of examples here, and maybe this will be a little clearer. So if we look at the 4000K LED products in the table, the range of products underlying these values have somewhere between about 2.4 to 3.6 times the ability of high pressure sodium to stimulate the IPRGCs. Okay, and incidentally, this is the value that I said that you saw earlier. If you go down to the 6500K, you'll see that's where you find that 5 times value that was cited in the AMA result. Let's take another example here. If we look at the 2700K products, they have a relative ability of about 1.9 to 2.8 times that of high pressure sodium. So these are not trivial things, but what I want to point out here is the overlap between these two ranges. So you see the lower end of the 4000K products have about 2.4 times the ability of high pressure sodium, whereas at the upper end of 2700, we've got some products up to about 2.8 times the ability of high pressure sodium to stimulate these IPRGCs. So what that means is that there are some 2700K products that are actually more of a concern in this particular regard than some products at 4000K. Again, this is just not a very precise indicator of what that ability is. And so if your goal is to minimize the disruption, the potential for disruption, simply saying, okay, we're not going to install anything above 2700K does not guarantee that you've actually achieved that. You really have to know the specific spectral power distributions for the specific products that you're considering and comparing to know how they compare, say, in this regard. Okay, so I've gotten pretty far down that rabbit hole. I'm going to climb out now. I just always also like to bring out everyone's favorite incandescent technology at about 2800 color temperature, and its corresponding relative melanopic potential is about 2.7, which puts it pretty firmly in the middle of the 2700 and 4000K products. So clearly, these issues that are being raised now have been around literally since electric lighting was invented, right? Okay, let me move on. So the discussion often seems to, almost all the discussion these days seems to revolve around the sort of the evils of blue light, but as a part of our natural diurnal spectrum, we should acknowledge that there are benefits too. So the Illuminating Engineering Society notes that there are some visual acuity benefits, for example, in a TM12 of blue wavelengths at the lower lighting levels, mesopic lighting levels that are typically found in street lighting applications. And this also appears to be supported by field research. So in this study, for example, this is from the conclusions, this study found that the spectral power distribution in the 4100K product they used in the study. Now, this is just one 4100K product, but that product resulted in the best overall visual performance of people that were the testing that they were running among the range of SPDs that were tested. I should also point out, though, that they also tested higher CCT products, so there's more, and they did not perform as well. So there's more to this than just spectral content, which is kind of true for all of these points that I'm making. It never comes down to just one thing. There's always multiple factors that wind up impacting the final result. Okay, blue is also a significant component of the natural spectrum that our eyes have evolved around, so it of course plays a role in making things look natural and also helps increase visual contrast, which has unequivocal safety benefits, right? Anything that further helps you distinguish, say, an object in the road from its background, the safety benefits of that are undeniable. So here we're looking at something I hope you don't see often while you're on the road, but this is an aviation cocktail that my wife has lovingly dubbed the purple thing, but which becomes something else entirely without the benefit of blue content. I just pulled the blue content out of that picture, and it actually looks like something we're lighting with high pressure sodium, right? Okay, the final point I want to make along these lines is that despite a popular misperception, when all things are equal, warmer color temperature LED chips are less efficacious than cooler color temperature chips. So this is due to just simple conversion losses from increasing the phosphor content to convert the initial blue wavelengths produced by the chip into other colors that then mix and emerge as white to our eyes. Lower or warmer color temperatures require more phosphors and more conversion, and thus incur greater losses. If everything else was exactly the same, which is never the case, but we're just talking theoretical here, if everything else was exactly the same, this would be manifested by a lower lumen output of the warmer chip, which means that to achieve a given level of illumination, you would have to increase the wattage to get that same level of light output and meet that same spec with a warmer chip. Okay, now you can see some pretty significant differences in this table that we assembled from cut sheet data from seven major manufacturers back in 2015. If you watch the right-hand side here, I'm just briefly highlighting a few of the largest percentage changes. This table is already out of date. This is a pretty fast-moving technology. It's 2 years old now, and manufacturers have, since even this table was produced, they found other tricks, if you will, and I don't mean that to be pejorative, but other ways of altering the light output so that this difference in lumen output is lessened. And for example, one way is sacrificing some of the color rendering ability of the chip. So maybe dropping from an 80 CRI for the 4000K to a 70 CRI for the 3000K, and they recover some of that difference in output. Maybe this isn't very important in many outdoor lighting applications, how well it reproduces colors, and if it reduces the difference in output from, say, 20% to 5%, a user may be happy to go with the lower color temperature, and that's fine. And it might seem like splitting hairs from that perspective, but this is not an apple-to-apples comparison. So, for example, the manufacturer could similarly drop the CRI of the 4000K unit to 70 and regain that efficacy increase. I know this question's come up among the folks in this audience, so the technical answer is warmer color temperatures use more energy, all else equal. That's just a physical property of the way these colors are, different CCTs are produced. The practical answer is, if you're willing to trade on some other qualities, you can get energy performance that's close. And you may even find 3000K products from one manufacturer that are more efficacious than 4000K products from another, just like we saw in that table. There's all kinds of variation out there in what's on the market. But again, these are not apples to apples comparisons. All right, now I want to change it up a little bit here and talk about sky glow. The increasing brightness of the night sky from anthropogenic light sources has been a focus of concern to groups like the astronomical community for literally decades. I think the first reference I saw, the earliest reference I saw to this was in a paper that I think was published in the 1930s. So they were already starting to pay attention to this as communities and so on started getting illuminated. The AMA release also brought this subject up. Sky glow both reduces the visibility of the night sky and also has these various potential environmental and biological impacts. This quote from two of the AMA release's principal authors really suggests more concern regarding sky glow than health impacts. And in fact, at least one of these authors was on the board of the International Dark Skies Association for many years. Sort of similarly, here's another quote I've heard or seen in articles more than once, sort of bemoaning the coming disaster from our ongoing conversion to LED streetlights. This kind of, these are common among people in the astronomical community, and like you can see in the photo there, I mean, this is a real concern for them. But these kind of statements typically appear to be based whenever there's any underlying information that's provided on the same kinds of faulty assumptions that I mentioned before, such as simply substituting a spectral power distribution from a high-pressure sodium product to a high CCT LED and then holding everything else constant. So at DOE, we thought, okay, what do we actually know about what's occurring in a typical street lighting conversion today? I mean, we do know there's an increased short wavelength content as we install these broad spectrum sources, certainly, and short wavelengths scatter more readily in our atmosphere than longer ones, which means there's going to be a greater tendency towards sky glow. But we're also seeing other characteristics change, like the output of the fixtures and the elimination of uplight. So when you look at all these things together, what's the collective effect of all of these factors? So this inspired DOE to conduct an investigation of its own, which we published earlier this year. This began with an extensive literature review, and we then recruited some internationally known sky glow modelers to help us investigate the scenarios that we thought represented the typical situation in the United States. So before I get into the results of that, I want to sort of begin here by setting the stage with a little bit of evidence for how we came up with some of our underlying assumptions that were made in that study regarding what we believe represents a typical conversion in the United States. And I want to emphasize that's the typical conversion. Your mileage may vary. If you try to look at these results in any particular location, they may be higher or lower than this, but we feel pretty confident that this is a representative of a typical scenario. Okay, so two of the primary factors responsible for sky glow are actually visible in this photo from Los Angeles. The first of these is uplight. So since we're looking down at these lights from above, everything you can see here is uplight, and this angle just above the horizontal turns out to be the worst for sky glow, because this light traveling along that pathway has the longest potential path through the atmosphere, and thus has the largest opportunity for scatter relative to, say, light going straight up, which in contrast is the shortest path through the atmosphere with correspondingly less opportunity for scatter. So that light basically penetrates the atmosphere and goes off into outer space somewhere, scattering the least. Okay, a second factor that's evident in the photo is significantly excess light output from the luminaires, which is largely a function of the older glass lamp technology used that produces light initially going in all directions and has to be significantly redirected and reshaped in an attempt to fit the target road surface beneath, right? The target is sort of this long rectangle that runs underneath these poles, and you're starting out with this light source that's throwing light out in all directions. So that's the purpose of the fixture, which contains reflectors and secondary optics and so on. It's very difficult to do this precisely. and which is very evident here from the hotspots underneath each of these poles that essentially represent wasted light, as does actually the uplight that we can see coming from the fixture. This is all light that we're producing and paying for, and it's doing nothing useful for us. In fact, it's just causing problems. All right, now let's compare that with the LEDs that replace those high-pressure sodium lights. Clearly, they're much better at putting the light where you want it. Note that there's near disappearance of not only those hot spots underneath the poles, but also there's an obvious reduction in uplight. There still is a little bit of uplight. It's now mostly composed of either there's a little bit of reflection from the poles right underneath the lights, and then also from the road surface. So this improved distribution that LEDs offer means vastly improved use of the lumens that are being produced by the fixture, and thus you don't need nearly as many lumens to do the job. So the LED luminaires in the right photo, these are real numbers, in the right photo put out less than half, well less than half in this case, the light of the high pressure sodium system they replaced in the left photo. And it turns out that this kind of reduction is fairly common, and we haven't done an official survey of sites, but we've worked with a lot of street lighting conversions across the country, and reductions in output seem to average somewhere between something like 40 to 60% on a per luminaire basis. So our study therefore just took this down the middle and assumed a reduction of 50% as representing the typical US conversion. So now I just want to quickly illustrate what that elimination of uplight looks like from above. So here's a photo that was taken actually just last week over Seattle on the way into the airport. And I like this photo. There are quite a mix of sources visible here. So to begin with, there are both 0% uplight luminaires and what I will call not zero uplight luminaires. So to start with, here are a couple of streets. These are both examples of 0%, if you can even pick them out. There's a street, the lower one there is LED, and the upper one is high pressure sodium. You can't actually see the individual luminaires. You can just see those little areas of reflection coming from the street. Now contrast these with some of the not zero uplight luminaires, such as these globes, which are off to the right there. I actually asked one of the street lighting facility people what those lights were, so I know those are globes. I'm sure that elsewhere in this photo there are also older Cobra heads that have drop lenses and so on, but I can't tell you which ones those are. But then I also want to call your attention to these other obvious sources, like the port facility there at the upper left, and of course the 800-pound gorilla here. That is Seahawks Stadium, where there just happens to be a game on at the time of this flight going over, which it was actually the reason for taking the photo in the first place. So the question here that I want to raise is, looking back at all of these areas with 0% uplight luminaires, and actually you can pick out others in here too. If you look down there in the lower left-hand corner, you can see some parking lots and things down there where you can see some reflection, but you can't see any of those individual luminaires. Yeah, there continues to be reflected uplight, just as we saw in that LA photo. That in the case of LEDs happen to contain more blue wavelength. You can see when you look at their reflections, there's a little bit more shorter wavelength content than the high pressure sodium that you can see if you can refine that street that I pointed out earlier. But are these lights, any of these lights, are these still a primary concern in the larger context of the collective amount of light that's entering the night sky from this area? Right? I mean, you've got numerous other incumbent sources and other things that are contributing. So how far do we need to keep pushing these street lights before we say, okay, enough, we're going to start addressing maybe some of these other applications? Okay, so now I want to get back to our SkyGo investigation. The model we employed here, this involved a lot of modeling, as I mentioned earlier. The model is very complex, and if you want to learn more about it or the results that I'm about to describe, I'll just refer you to our couple of webinars that are posted on the DOE website on that address I showed before. I think we have a pretty good explanation of both the results of the study as well as we have 2 webinars, and the second one goes way into detail on the aspects of the model. Or you could always go look at the report itself if you've got, I don't know, 10 or 15 minutes. So in a nutshell, we modeled several different variables, running the model once for every incremental value. So in the end, we have a run that represents every single combination of every value of every variable. And in total, this required more than 215,000 runs of the model. So we also brought in our supercomputing resources at the lab, so we wouldn't have to wait, weeks and weeks to get our results. So among the most important variables that we found were those that I've just sort of highlighted, the spectral content, which we modeled in the form of different products and CCTs, the light output from the luminaires, level of light output, and the percent uplight. So now I am basically jumping to the very end of the study. So imagine this is a 400-page whodunit, and I'm just going to tell you right now that the butler did it. Okay, so we're just going to skip all the deadly detail that led up to this revelation. So among other findings, we determined that while increasing short wavelength content, which also typically but not always, typically corresponds to increasing correlated color temperature, while this does tend to also increase light scatter and thereby augment the contribution to sky glow from a streetlight, the actual ultimate impact is typically more than offset by other accompanying characteristics of the conversion. And that's what these 2 charts are showing. So basically, the largest potential sky glow impact to positions near the city, which we modeled as being right on the perimeter, right on the edge of the city, comes from reducing the lumen output from the luminaire. Okay, so if you remember those, basically we're looking at that little amount of reflected light underneath the luminaire, and all of these impacts are being basically compared, being shown relative to a high-pressure sodium baseline. Again, these are relative charts, just like the earlier table that I had, and that's depicted as that dashed red line at the value of 1.0. So we called a 50% reduction in output typical, and that's what we modeled, but this relationship is actually linear. So if you cut output by 50%, you get a 50% reduction in the contribution to sky glow. If you cut output by 75%, you get a 75% reduction, etc. But again, these are all just individual variables in here. All of these influences get combined to produce the final collective set of results that you're seeing here. So at our modeled 50% level, the reduction in sky glow following a conversion typically more than offsets any increase from changing the spectral content until you get to very high color temperatures like 5,000 or 6,000 K, if you can see my cursor here, like over here. That's when you start to see, relative to the high pressure sodium baseline, when you start to see some increase. These are not being commonly installed in the United States. And even this impact is focusing only on the effects specific to the human eye, i.e. we are looking at the scotopic weighting of these results. This is reflecting the fact that our eyes are not equally sensitive to all wavelengths in the visible spectrum. So there's an action spectrum, just like the one we saw earlier for melanopic, there's also a scotopic action spectrum. And that's what these results on the right show there. So now for a distant location down here on the bottom, which in this case we modeled at 25 miles from the city center, getting rid of the uplight from the luminaires had the largest single influence here. This all but eliminates the contribution from the streetlights to sky glow at that position, regardless of the short wavelength content or CCT, and regardless of whether you're looking at unweighted or scotopically weighted results. Okay, if you think back on the LA photo, for example, we had a little bit of reflection coming from the ground. If there's a sufficiently high short wavelength or blue wavelength content in that, you can possibly increase the local sky glow immediate to that area, right around where those lights are located. That increased blue content can result in a slight increase in sky glow. But that light just does not travel very far. It quickly dissipates. So as soon as you get outside of the city, We only modeled 2 locations, one at the edge of the city, one 25 miles out. We don't know exactly. I'm sure you don't have to go 25 miles to start seeing these kind of results, because that light just doesn't go very far. But basically, once you get to 25 miles, the kind of reductions we're seeing in this chart are 95% or greater reductions compared to the high pressure sodium baseline that was replaced. Okay, and I just want to also reiterate this point that I showed in the Seattle photo earlier. Street lighting can be an important contributor to the concerns that are being raised, but in some cases they're not even the primary source. Now, actual data estimating the contribution of street lighting compared to other sources, like how much does street lighting comprise compared to buildings or other sources, actual data is pretty sparse. These pie charts show one estimate that was made from a pretty respected researcher, Chris Lugenbuehl, back in 2009 for Flagstaff. The left side there includes a sports stadium that isn't lighted all the time, but when it is, it actually comprises almost a third of the city's total all by itself. These are estimates of not of sky glow, but actually of the amount of uplight coming from the city and what those different sources are. So that's maybe not a surprise, given looking at the earlier Seattle picture, that sports lighting is a third all by itself. When those lights aren't on, then commercial lighting, which includes things like parking lots and building facade lighting, etc., make up a little bit more than half. So Flagstaff isn't a typical city. They've had dark skies concerns because of the observatories that they have there. They've been focused on that for decades. I think they started in the 70s. They implemented some kind of dark skies policy. But the main point here still stands that, if we find, as a society, if we find light outside our windows at night is a significant concern, then reducing it is going to take a lot more concerted effort than just targeting, one single application here, street lighting, which may not even be the majority one in various instances. That'll definitely have some impact, but it may not even be noticeable in the larger context of things. Now, like the typical human eye requires a change in luminance of about 30% to even be able to detect it. So if you look at that right chart there, roadway lighting is only comprising about 12% there. That means you could probably turn those street lights off. And if you were standing outside of the city and looking back at the city, you probably wouldn't be able to tell the difference looking at the sky globe. So these are just important points to keep in mind. Okay, so speaking of which, now I've thrown a lot of information out here, I know. There's just a few thoughts that I guess I'd like to have you take away from this presentation based on what we've learned and what we're seeing around the country. The issues that have been raised definitely warrant further investigation, but the implied risks and concerns may be overstated. Here I'm taking a page out of the AMA book. They may be overstated given current understanding and uncertainties. There's good news here that the typical street lighting conversion in the US today is likely already improving the situations of concern. So typically we're seeing reduction in output and elimination of uplight. So these are addressing a lot of the issues that this presence of this light at night that has been kind of the subject of a lot of this concern. Despite this fact, some users may decide, some users are deciding that the politically expedient approach is just to follow the recommendations regardless. And for example, just don't install anything over 3,000 K. And a good example of that is Chicago, who recently basically agreed to just concede that point. They just didn't want to spend a bunch of time wrangling with a noisy group of people that were raising concerns and so on. And that's really fine from our perspective. That's as valid reason to go with a lower color temperature as any, actually. We recognize that cities are trying to achieve a balance among many competing objectives, and sometimes different ones take different weights and so on. And if they say, you know what, this will just make this problem go away, Otherwise, we're probably facing a lot of delays, etc. We're just going to go with it. We're fine with that. From our perspective, DOE, and I think the lighting community's perspective, we just want people to understand that there are going to be some trade-offs, understand what those are. All the information is on the table, and then go ahead and make your decision. And that's fine. You may choose that, okay, we're going to use a little more energy, or we're going to give up this or that, or do whatever. It's fine. We just want that we just want that decision to be an educated one. Fortunately, LEDs continue to expand their ability to meet the demands. And so, for example, I mentioned the manufacturers earlier that are coming up with new tricks to basically reduce the difference between the lumen output by maybe compromising some on color rendering ability and so on. Also, they offer really unprecedented ability to engineer the spectrum. We're even seeing color changing products out there now, right, where you can actually change it live. It's probably, I don't know how likely it is that some of those will ever wind up in street lighting applications, but it just gives you an idea of it illustrates the kind of flexibility that this technology has. And so this is going to remain, LEDs are going to remain the best solution available today and into the foreseeable future. And then when you combine them with things like control systems, we see, well, this is a point specific to control systems. I want to say that, due to their value on multiple fronts, which includes dimming capability, DOE strongly supports the addition of control systems at the time that streetlights are converted to LED, because the cost effectiveness argument is never going to be better at that time. And unfortunately, we see, of course, a lot of cities are saying, well, we can get 2/3 of the savings if we just do the lights themselves. We just substitute the lights, and then we get a 1 or 2 year payback on that, and the control system has a much longer payback. I guess we'll wait on that, but the problem is that you've already captured the bulk of the energy savings, so it just becomes that much more of a hurdle to try to justify these down the road. I liken this to smartphone technology. So imagine if you could step through the time travel portal and talk to some of your friends 20 years ago, and you were trying to explain to them why anybody would want to spend $1,000 on a phone when they, whatever the prices they were back then. I mean, they couldn't visualize it without all the apps and just all the other features that these things have brought. I think this is actually a pretty good analogy for street lighting. It's going to take a lot longer for that stock to turn over, because it's much longer lived than your typical cell phone. But I firmly believe that in 25 or 30 years or 35 years or whatever, that cities wouldn't even consider putting in lights that don't have some kind of these smart capabilities, because of all of the other benefits that come from having those. Just one of those is dimming capability, which does save a little bit more energy. It does save a little bit of money, but it also can be used, for example, to address some of these other kinds of issues. Like I said, that there's a linear relationship between reducing the light output and reducing local sky glow. If this turns out to be a big issue, cities can address it immediately. In fact, Chicago, out of they're replacing something like 300,000 lights. They've so far replaced about 12,500 of those. I was just on a call with them last week. They said they have already started using some of the dimming capabilities on an individual basis. So where they're getting complaints about how there's too much light maybe at a particular location or something, they're able to address that immediately with their dimming system. So we strongly support the addition of control systems at the time that the lights are converted to LED. I know that's a tough sell, but we should do it. Okay, so that's it for what I had to say. I think we still got a few minutes here left for questions. I don't know. Actually, I don't. Okay, I just see one question in here right now, which I'll answer here in a second. If you think of something afterwards, you can email me at that disguised email address there at the top of that page. And assuming I don't get flooded with these, I'll try to get a response back to you within the next day or two. Okay, so this question is asking about the range. So what about 5,000K? What about 5,000K? see, I don't know if I can see the rest of this question. A lot of outdoor lighting, maybe that is the whole thing. A lot of outdoor lighting is 5,000 K. So it's going to be somewhere in between, obviously. If you look back at that table, you could do this later. If you look back at the table that I included, you can see what the corresponding ability of those of virtually any color temperature is, how it compares with high pressure sodium. But the important thing, one of the most important points that I want to convey here again, is that that is just one factor pertaining to these concerns that have been raised. And so, like, if you look at the SkyGlow study, once you get rid of the uplight, you know, basically that problem has pretty much gone away across the board for all the color temperatures. Once they got rid of the uplight, again, you can reduce even local. If someone's got a light shining right in their window, I mean, you could maybe you do this on a schedule, so maybe after midnight or something, you cut the light output by 50%, like they're doing in Cambridge, Massachusetts. That would cut the person's exposure by 50% just by itself, just by dimming those lights. You know, this is one input out of many factors that that pertain. Oh wait, let me see. Are there some more? I might have some more questions. Okay, is there a study that looked at the impact of LED lighting on wildlife, i.e. birds, and then chirping at night? What are the negative impacts? Actually, I've heard of another study. I'm not familiar with this one. There was another one that was measuring impact, recently came out, that was measuring impact on migration patterns, and the way they were determining that was they were listening to the signaling that these birds do as they were flying over the lighted area. This particular study had to do with the 9/11 memorial in New York City, and if you've seen that, it's got these two huge beams that go way up into the sky somewhere, and really it's no surprise that it was disrupting birds that are flying through there. I mean, that's kind of an extreme case. And so I don't know. Yes, light at night, and this is like an example where SkyGlow can affect things, where birds are flying near cities. Sometimes that increased brightness of the night environment causes some disorientation, I guess, and so on. And sometimes they can circle these cities and have issues from that. But it's also there's variation from species to species. So sometimes the actual colors that affect different species differ. So you can't make like a blanket statement about the kind of impact that would occur from one given light source. You know, and there was another study that just came out last week, and we've been in contact with the author, the lead author, who's in Germany, who actually know via email anyway. And it's a good study, but it's looking at it's taking photographs from the VIRS satellite and looking at light penetrating into space. And the media again has run with this as being, you know, the amount of light coming from the Earth is increasing, according to this study, at about overall about 2.2% per year. But there are some notable variations in there, like the United States, which didn't change at all, despite the fact that this was a difference between 2012 and 2016 is what this particular study was looking at. That happens to correspond to the time frame that the United States installed or converted. Most of the conversions that have taken place of streetlights have occurred in that time frame, 2012 to 2016, and they're by and far 4,000 K. The 3,000 K hasn't really come out in any significant way until the AMA thing came out in 2016. So really, we're just starting to see those lights going in right now, and yet they didn't measure any change in the United States. This is a function of some of this. It doesn't necessarily all represent waste, is the main point that I want to make here. We need light to bounce off objects in order to see them. Some of that light is going to reflect off into the night sky. There's just no way to avoid it. If we're going to have lighting, if we're going to light our environment at night, if we're going to have buildings that have light coming out the windows, all of this, some of that light's going to wind up in the night sky. We have lots of developing countries around the world that are trying to come up to our standard of living. Their GDPs are increasing. They're putting in more buildings, putting in more roads, putting in, you know, and getting benefit from having those light sources. The overall the situation in the world is that that light at night is going to increase. This is kind of an evil of, just like many other things that humanity does. There are negative consequences of the actions we take. What we can do, the best thing we can do, is try to minimize or eliminate wasteful lighting practices where we've got light, like I was showing, where we have uplight or we have excess light bouncing off the pavement. It's not doing any good. It's just causing these problems. We might have light spill, lights that haven't been properly designed. The distribution hasn't been properly matched, say, to the location, so you got light shining in someone's window or something. These are all fixable problems. We should be fixing these problems. We should be not putting more light on the street surface than is actually needed by the application. And maybe if we can employ dimming systems in the future, this is the best that we're going to be able to do. Despite all of that, when the rest of the world comes up to our standard of living, or even approaches our standard of living, the overall light output from the world, what's going to be going out into outer space, is going to increase. I just don't see there's any way around that unless we just turn the lights off. Maybe when we have autonomous cars and things like that, for example, we won't actually need any, or we'll only need very minimal amounts of light on the street. So maybe there'll be some other technological solutions that'll come along that will affect these things. But this is largely a function of our increasing civilization. So I guess let me take one more, if I've got another one. Okay, so let me take one more here. I'm running over a little bit. Does glare have any significant impact on circadian rhythm, and should the manufacturer's bug ratings, no, I'm sorry, that was the end of another, this question actually ended halfway. So glare, it's more a function of intensity. So in terms of glare being a measure of intensity, if someone's got a real glaring light, they're getting a pretty good level of exposure from that source. So yes, that could affect circadian rhythms, but it's really the intensity of the light source, which is what we're talking about. So for example, you can have, you know, annoyance glare if you're standing up at the top of the Grand Canyon and someone's down at the bottom with a LED flashlight and they shine it towards you. That's actually a form of glare, this annoyance glare, but it's not going to, you know, it's not going to disrupt your circadian rhythms or something. So glare is more like an indicator of the exposure, of the intensity level, but it's actually not the direct measure of that. Okay, so Heidi, I think we're over. I've got some other questions here, I guess. I'm sorry, they've moved off the panel here, so I wasn't able to see all of these. But what I'll do is take a look at these after the fact and try to respond to any that I have here. Maybe I don't know if they probably don't identify who they came from, so maybe I can just provide them to you, Heidi, and you can post this with the presentation after the fact. Thanks.
Okay,
Thanks very much.
That sounds good. Thank you.